About a month ago, a new brushless DC motor was released for use on drones, and the motor boasts some pretty impressive performance increases over pretty much every previous mini quad motor to have existed. And the performance boost is all thanks to what the designers are calling an optimized magnetic design. And I'm going to be using the ANSYS magnetostatic analysis tool to look at some of the design decisions that they used in making this motor and try to see why they could have an improvement on the overall performance. So in a typical drone motor, there are a bunch of magnets kind of surrounded by a central stator, and that's just the motor. But the difference of this new motor is that it has these things called what they're calling flux rings, which are these little steel rings that kind of just go on either side of the magnets. And so in this very simple model of the motor, I've added those steel rings, and I've also modeled a motor with 14 magnets and 12 stator poles. We're going to start off in the analysis systems by dragging in a new magnetostatic study, and then we can go into our engineering data. And I'm going to start by deleting the two default materials, and then we're going to add the custom materials, which will be an air material and then a neodymium 35 magnet material, which we'll call ND35. And then for the air material, we can drag in an isotropic relative permeability, and we'll set a value of 1, and the unit can be left blank. And then for the neodymium magnet, we'll go into our linear hard magnetic materials and drag in a coercive force and residual induction. The coercive force is going to be 9e to the negative 5 amps per meter, and the residual induction will be 1.2. We're also going to open up our engineering data sources and open up the magnetic materials in the magnetic BH curves, and I'm going to select the M19 steel variety. So we can use the little plus button to add it to our materials list. And if we go back to our materials, you can see them here. And I've also made sure that these materials don't have any additional material properties. It just has the magnetic ones. So we can go back to our project and open up the geometry in SpaceClaim. And in SpaceClaim, we need to, you can see the rotor here with the magnets and the stator and the flux rings. So we need to add an enclosure. So if we go into the Prepare tab, we can add that enclosure. And then we need to select all the geometry that we want the enclosure to include. So all the magnets, the stator, and also the flux rings. And then we can change the type to cylinder. We also need to select the axis that the cylinder will be around. So we can just select any vertical edge here. And then I'm also changing the default cushion to 15% just to save some computational time. And then one important selection that we need to make is we need to change the share topology to share rather than none. Back inside the workbench, we can open up the model tab. And so you can see our imported geometry here along with the enclosure. If I open up the geometry tab, you can see some of the parts. And I'm going to go ahead and rename some of these for simplicity. So we've got both the lower and upper flux rings. And then we can also rename each of the magnets just numerically from 1 to 14. And then we've also got the stator in the center and the enclosure. And I'm also going to select all the magnets and assign the material to our neodymium material. And then for the flux rings, they're going to be assigned to the M19 steel along with the stator. And then the enclosure. And then the enclosure will be set to the air property. And then for the magnets, there's a property to specify the polarization. And so we need to go in and define a coordinate frame for each magnet that kind of dictates which direction the magnetic field points in. So I'm going to go ahead and hide the enclosure, the stator, so we can get more access here. And then for the first magnet, which is this one over here, I'm going to select the face, and then we can define a coordinate system in the coordinate system tab. So we'll add a new one. We'll click on the face and use that as the origin, and we'll specify the X direction with a geometric selection. And so now we've got like the X direction points normal to the magnet face. So now in the geometry, we can click on the first magnet, and where it says coordinate system, we can choose the system that we just made. And I'm actually going to go ahead and rename that coordinate system so it's more clear. If we go back into the coordinate system tab, we can change it to be named 1 to match the first magnet. And you can see that that change propagated here. So now we have to repeat that for the second magnet. So again, the process is just to create a coordinate frame that has the X direction pointing inwards towards the center of the circle. And then we'll just do that for all the magnets and then go ahead and assign it for all the different magnet bodies. So here you can see I made all the coordinate frames and they all have this X pointing normal into the center of the circle. And then I'm going ahead and assigning all of the magnets to their respective coordinate frame. And then we also need to take every other magnet and flip the direction because the motor, all the magnets kind of have opposite polarity. And so I'm taking all the even magnets and changing the direction to X negative rather than X positive. So now all the magnets have their magnetic fields aligned in the proper direction. So we can move on to the meshing step. Once I re-show all these bodies, I'll start by just generating the default mesh and we can see how it looks. And to get a better look inside, we can hide the enclosure, or we can also make a section plane view. So we can just draw a horizontal line and use that as a section plane and take a look on the inside. And the default mesh is looking okay, but we're going to do a little bit of refinement. So if I turn the second plane off, I can hide the enclosure and get a look inside. And what I'm hoping to do is add a little bit of refinement on the flex ring and the magnets themselves, since the elements are kind of very few in those areas. So to do that, I'll add a sizing method and I'll select all the geometry that I'm going to refine. And then I'm going to set the sizing to 0.3 millimeters. And once we update the mesh, we'll see that it's looking a little bit more fine. Is good. There we go. And then the last step will be to add our boundary conditions. So that's set in the magnetostatic section. We just need to add a zero flux, like no flux boundary to the outside surfaces of the enclosure. And once that's set up, we can go ahead and run the study and generate the solutions. From there, we can start to define some results. So I've added a magnetic field intensity result and evaluated it. And then we can look at our section plane view again to take a look on the inside of the magnets and the stator. I'm also going to turn on the smooth contours and remove the mesh lines so we can see it a little bit more clearly. And so this is kind of an interesting result that just shows us what the actual field intensity is inside the magnet and inside the motor. I'm also just going to add a flux plot now for the total magnetic flux. And once we evaluate that result, we should be able to see, this will actually show us like what is inside the actual stator coils. And so this is a pretty interesting result. You can kind of see the places where the magnetic field cancels out and also where it kind of adds together to form a really strong field, which is quite interesting. And I'm also going to add a geometric path that we can then plot along. So I'm going to specify a start coordinate at the center of the motor, and then the end coordinate will be kind of radially outward through one of the stator poles. So the y coordinate will be the same, but then we'll change the z coordinate. So you can see that line kind of through the motor there. And then if we define a new magnetic flux density, we can plot it along that path. And that will give us kind of like a data curve of the field strength through the stator of the motor at its kind of maximum point. So we'll just change the scoping to the path that we just defined. And when we evaluate that result, we should get a little graph. There we go. And so you can see that the highest magnetic flux is kind of like right in the center of the core of the motor stator. So it would be interesting now to compare that total flux to a case without the flux rings. So I'm going to duplicate the project, reopen the geometry in SpaceClaim, and I'm actually going to delete the enclosure since we're going to have to remake it without the flux rings. So I'm just removing it, and we're going to go up to the flux rings and delete those two components as well. And then just like the first simulation, we need to remake the enclosure. So again, that's in the Prepare tab. We'll just kind of speed through this part. So you just click the enclosure, select all your geometry. So then inside of the Mechanical tab, we can reset the enclosure material assignment back to air since it lost its reference. And then we can generate the mesh for this new model. And we also need to make sure that we change the magnetic flux parallel boundary condition since we did redo the enclosure body. So once we apply that, we can run the study. And when it's finished running, we can take a look at the results. All these are basically the same, and we won't be able to see a huge difference. But one of the things that I am curious to look at will be the total magnetic flux along that line that we plotted earlier, and we can hopefully compare that between the cases with and without the flux ring. So to do a good comparison, I'm going to grab the tabular data that kind of is plotted along the line, and then I'm going to make a graph to compare it to the case with the flux ring. So I just go up here and copy it into an Excel sheet. So here I've kind of copied that data in, the radius, and then the magnetic flux for both the normal and the flux ring case. And then I've made a plot of that. So what's pretty interesting is that we can see, let me just make it a little bigger here. We can see a notable increase in the magnetic flux in the core of the stator when we add the flux ring, which is quite interesting. And if we actually want to kind of quantify the kind of increase in magnetic performance, maybe what we could do is we could, let's see, we could calculate the maximum flux in both cases. So if I just calculate the maximum of the normal case without the flux ring, and also the maximum of the model with the flux ring, then we can calculate maybe a percent difference between these two. So select that. Oh, need to multiply by 100. And so we see that we get about a 7% boost in magnetic performance when we add these two little metal pieces, which is a pretty interesting result. So even though this analysis was rather high level, it still has some pretty important and meaningful results. Namely, it shows that magnets are pretty sensitive to the materials that are around them, and even adding a very small, lightweight little steel ring to a motor can have actually a pretty important effect on the magnetic performance. And so when you are designing a system that has magnets, performing some sort of magnetostatic analysis could be really helpful to try to kind of squeeze out as much performance out of the system as would be possible.